Hey students, I wanted to show you some more supplemental ones from chapter 18. And this is from the harder book, the University of Physics. So this involves a little bit of calculus. This is a good one to see. It's a bit advanced, a bit complicated, and one that I was working up to. And my supplemental only went to an hour and 17 minutes, and I thought that would be enough to stop. So let's take a look at this one. This is the one that I was referring to in the lecture, that we have a rod of length L and of charge Q, and there's some point P and a distance away from the point P. And it says here, the charge per unit length on the thin rod is shown below as lambda. Okay, so let me stop right there, because as it says, charge per unit length. This was my comment in the lecture about looking at density. This happens to be charge density instead of mass density, as we talked a lot about in physics 110. But you could do something like this. You could take the whole charge and divide it by the whole length. I'll call that lambda. But that would also be the same as a little charge over a little length. And here's where our calculus is going to come into play. Let me just kind of take a little section of the rod and then say, okay, that little piece right there has a charge of dq in it, and it extends a length of dx. So in other words, we could call a little bit of charge divided by a little bit of length its density also. And they would be equal to each other. So this was my comment about a candy bar, where you can take the whole candy bar and divide by the whole length, or you could take one little square of the candy bar and divide by its length. You're going to get the same ratio. It's the same or a uniform density here, and so that's what they say. The charge per unit length is given by this lambda. Now, the reason that's important here is because the question goes on and says, what is the electric field at point P? And then they give us a hint. Solve this problem by first considering a small electric field due to a small segment of dx, which contains this much charge. In fact, that right there is their hint. So a little bit of charge would be the charge density times the dx. And the charge density would be Q over L times dx. So that's going to be kind of this magical step, because then we can say, okay, well, let's look at the electric field. And we've been drawing the electric fields in blue, at least your author has, and so I'll kind of switch over here to blue and say, okay, the electric field would be pointing something like this from this little chunk of charge, assuming it's a little positive one. And then if we extend our calculus, we would say, well, then there would be another chunk of charge and another chunk of charge. In fact, we should probably start here and say that's the first chunk, and that's the second and third and fourth and fifth. And so there's eventually an infinite number of little chunks of charge. But the hint says, look at just that one chunk. Okay. So remembering that the equation for the electric field is Coulomb constant times the charge over r squared, we could then say that a little electric field, I'll call it dE, so a little electric field dE would be equal to Coulomb's constant times that little bit of charge over r squared. And that's the hint, because then it says, then you can find the net field by integrating over the length of the rod. In other words, now we have to add them all up. And that's what an integral conceptually is. So if I put a little integration with both sides, then the integral of dE is E. So that's kind of the big step. Then we have this integral, and of course dq doesn't really make a whole lot of sense in terms of mathematics. You really need to change that into the x-axis. And that's why the hint was so important, because knowing a dq is related to a dx, and then there's this density factor, we can then replace this, and I'll just go lambda dx for now. And then later on, I'll put the lambda as Q over L. In fact, we could probably then look a little closer at this integral and say, all right, now as I add it up, I have a dx. I can add it up now over the length of the rod. And I would then be thinking of my first chunk of charge at a distance of a, and my last chunk of charge at a distance of a plus L. So I'll put my limits here and say from a to a plus L. And there's my dx. So that's kind of the numerator. Two constants I can pull out in front, the dx and the limit. Now this r is the distance away. And so I guess that is the x. And so, again, my distance away would first be a, and then it would get bigger and 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 bigger until we got to a plus L. So I'll just call that the distance away. Might as well call it an x now, since we're looking at a horizontal axis instead of a radius. So I'll just... Same idea, instead of calling it an r, though, I'll call it an x so that it matches. And so now I can actually do an integration, although maybe I will write it as x to the minus 2 dx first, because when we integrate a power function, we add 1 to the exponent and divide by that new one. Then we've got the limits a to a plus L. So a to a plus L. And so then we can put, and I'll put the minus sign with the k lambda, and then I will go a 1 over x minus a 1 over x. So this would be a plus L minus a. And so those are my limits. And I suppose I'm not a big fan of the negative sign out in front, so I will incorporate the negative sign. And so the 1 over a becomes a positive, and this one becomes the negative. So that'll just switch the orders. And I suppose then kind of the general rule is to leave it in the quantities of the dimensions, and so we can debate if we should leave it as a lambda. They did give us the phrase lambda, but generally the rule is you should give your answer in terms of the variables that were given to us, and technically they gave us a lambda, but that was kind of a hint, and so they were really saying use the q over L. So I think we need to make sure we put a q over L for the lambda. But the A is clearly given, and the length of the rod is clearly given. And so there is my calculus work. So it's not a long problem. It took under 10 minutes, but it is a calculus problem. And it says add them up. Now, by the way, I hope you noticed that in one sense I got very lucky, because the electric field from every little chunk pointed in the x direction. And so I didn't even mention that this is technically the electric field in the x direction, the x direction, the x direction. But everything's in the x direction, so I'm technically done. But a harder problem, I would have to do the same thing for the x component and the y component. Because remember, adding vectors, we have to get a component and then add x's to x's and y's to y's. And that's an important piece, because the second example I wanted to do, also out of the university physics book, is the next one. It's number 84. And number 84 is going to have exactly that challenge, that they'll be pointing in different directions. And so we need to give this some thought about direction and components more than distance. In fact, the point P is always the same distance from this half circle. So it's not about the distance changing, but it's about the angle changing. Watch, let's read this problem. It says, the charge per unit length on a thin circular ring is shown below. Oh, is blank. I think what happens when I copied it is it did not register. Let's see. Yeah, it says it is, and they call it lambda. Maybe that's why that lambda tried to print up there in the edge. Okay, couldn't figure out why that lambda was there. All right. So kind of the standard symbol for charge density per length. So the charge density per unit length of a thin semicircle, so got a half circle, wire is shown is lambda. What is the electric field at point P? And point P is at the center if this was a full circle. Okay. So maybe I'll go to my blue so I can draw the electric field, but it's kind of that same thinking that I would take a little chunk of charge, so let me call that dq. For the moment, let me think of it as a positive value because it would make an electric field something like this. And then if I took a grid, there would be a y component and a x component. And why don't I call this angle theta right here? Theta. And this is what I was saying then, that for this problem, like a lot of our vector problems, we need to look at the x component and the y component. And if, like the last problem, we think about the magnitude of this as dE, where, and I'll come back to the last problem, dE is the k times dq over r squared. So that's the magnitude of the field. To get the x component, I would have to go cosine of theta. And to get the, no, sorry, that would be the y component. To get the y component, I would go cosine theta. To get the x component, I would go sine theta. So I'm going to do this. I'm going to say, okay, a little bit of the x component is the magnitude of it multiplied by sine theta. And a little bit of the y component would be the magnitude times cosine theta. And see, that I did not have to worry about in the easier one here, number 18. All I had to do was to realize that the distance of each little chunk kept increasing. I didn't have to worry about the component. Although now on this problem, I don't have to worry about the distance, because if you look at some other little chunk right here, that's going to make an electric field kind of off in this direction. And so our angle theta is now a little bigger. But the thinking is still the same, that you're still going to have an x component, which would be the sine of that angle, and a y component, which is the cosine of that angle. And the magnitude doesn't change, because as we go around, each little chunk has the same distance away. So I would really describe 84 as kind of the opposite effect of 83. 83, we had the distance of the charges changing, but not the component or the direction. Here, we have then the component or the direction changing every little chunk, but we don't have the value of each little vector that we're adding together change. And so that's the trade-off here. Okay. So let's go ahead and start adding them up. And so I guess to get the total x component, I would then integrate my dx, dE sub x, which is integrating dE sine of theta. Whereas over here in the y, to get the total vector in the y direction, we need to add up all the components in the y direction. That would be this magnitude dE times the cosine of theta. Now, I think I mentioned this more than once, but let me say it again, and probably a lot of times, that if you kind of have not just a math ability to do these problems, but a conceptual one, you can save yourself a lot of work. And you really need to have both those skills. Because watch this, what I'm going to do for the x component. I'm going to say, oh, that's easy, that's just a 0. And the reason I'm going to say that is I'm going to look up here, and I guess I will finish drawing this vertical line. And then I'm going to look at a little chunk of charge that is just like this chunk of charge, but it is exactly the other direction from straight down. And I will call that the symmetric twin. But I do want to point out that every point on this semicircle has a symmetric twin. And if you look at the electric field from its symmetric twin, and so you compare this one to this one, you will see that the electric field has a vertical component, just like this one. So both of these have the same value of the vertical field. And it has an x component, but this one now has an x component to the right, or the positive direction, whereas this one had an electric field to the left. And then notice the x components are equal in magnitude in opposite directions, so they would actually cancel off. So as long as we have a symmetric twin, if we add them all together, we're just going to get zeros and zeros and zeros plus 0 plus 0 plus 0 plus 0 as we go all the way around. And so that's why I would say you add an infinite number of zeros, you still get 0. And so that symmetric property, and maybe I should say that intuition of focusing on the meaning of the field and that they're a vector, could make your math steps really simple. Because I didn't really even do any math. I just looked at the picture. And so that when somebody goes, well, how'd you get 0 out of that? Well, let me tell you, it's not from the math. I know it looks like I did some math, but what I really did was get to a point where I could then visualize what the x component would look like and realize that every point would have a symmetric twin, and therefore the twin and the original would be 0. And so even if you took some calculus and took the limit, you would still have just a bunch of zeros. And so you would have 0 plus 0 plus 0 plus 0 plus 0 an infinite number of times, but you're still going to get 0. And so the electric field in the x direction is 0. Nice. So we just saved ourselves a lot of work, because I thought we were going to have to do an integral twice, one to get the x component and one to get the y component. But it turns out the x component, because of the symmetry involved, comes out to be 0. Okay. So really the hard part of this problem is right here, one where we don't have a symmetric twin. As I did point out, though, the symmetric twin, if you want to call it, gives the same direction. So you could do this. You could say that if you took the magnitude of the electric field and you add it to cosine theta, and you add from here to here, and so from 0 to 90 degrees, I'm going to put pi over 2, that would give you the same vertical component as if you went from 0 to negative pi over 2. And so this has enough symmetry in it that what I can do is multiply it by 2 and say I will just go 0 to pi over 2. And that would be the vertical component of the electric field from here to here. So then if I just double it, that would take care of the fact that I got to do an interesting integral on the other side of the equation to find out what the total electric field is. So that's a big step. So that is my justification of why I'm doubling it and why I'm only going from 0 to pi over 2. Now I guess I could have gone from negative pi over 2 to plus pi over 2 and not have the 2, and I would just be adding up the whole semicircle. But it's neat to see that you could do it with a quarter of a circle and just double it, and that's a symmetry argument, because it really helps us then to understand the x component coming out to be 0 a lot better. Okay, so let me keep working on this this integral here. This dE, as we talked about earlier, would be Coulomb's limit or Coulomb's equation in a very small limit. So we would have Coulomb's constant and a little bit of charge dq and the distance away, which is r squared cosine theta. And so that is the magnitude of dE. And the cosine theta is what gives me the vertical component. And the fact that I go from only at 0 to pi over 2 means I do half of it, and the other half is going to be symmetric, and so I'll just double it. So that's where this equation comes from. And we can pull constants out in front. And so notice, and I guess I will put x squared down here, but this number also is a constant. And so if we think about adding this whole thing up here, this chunk plus 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 this chunk, and so forth and so on. As I go from 0 to pi over 2 and I add all these chunks together, I can say that the electric field from x would be giving me the same value. And that's what I want. I want the x component to come out to be 0 and the y component to become out something non-zero. All right, so coming back to finish this line, there's the 2, there's the Coulomb's constant, there's the r squared, there's the dq, there's the cosine theta. And so as we add it up, the angle does change, so we got a little bit of work to do. And then this is going to equal the total electrical field in the y direction. Okay. So I guess I have a 2 times Coulomb's constant times x over squared, or over x squared. And again, that's why I said we kind of got lucky on this one that the distance didn't change, whereas on this first one the distance did change. But also we got lucky on the first one because then the direction of them never came up. It never was an issue, and so we just added them together, all pointing in the positive x direction. But if it was an issue and we wanted to combine them together, we got to be careful. And in this case, they're all the same direction. But in this case, the one we're trying to solve now, they're not in the same direction. That's where this cosine theta comes into play. But at least it's the other thing, that the other side of this coin, that at least the value here stays constant. And so we get the Coulomb's constant, we get the x squared. That doesn't change. And now we can go ahead and actually then do this integral. Or at least we can attempt to do it. Maybe I'll write it this way. I started to write it here. So here's the 2k over x squared, and integral, and I'll go ahead with the dq, and here's this cosine theta. But remember the dq, and so let's do the lambda again. Lambda can be the whole charge, which they call q, divided by the whole length. Now remember, a circle is 2 pi r. So half the circle is pi r squared. So pi r. No, not a square, just a pi and an r. Okay, so there is the radial direction. Okay, or this will, trying to get the field, and I'm adding up radial components, but I only want the cosine of the angle. Okay, now we could say this is a little bit of charge over a little bit of length. Now let me pick a convenient symbol. When we did the straight rod, I picked a little length as a dx because it was along the x-axis. And that was convenient. Had the problem been in a vertical fashion, maybe I would have picked a dy. But what do I do when it's an arc? And so I would say, let's call it ds, where the s is the length of the arc. And again, why that can be helpful here. Is I can then replace this dq with lambda ds. And then it's 2k x squared. Now maybe I shouldn't have put that as an x. I did pull it out, but I think I probably should have used the distance away. And I see why I did the x, but let me call it r squared. R squared. Where r is this distance away, it is the radius. And that's what makes this problem nice, is that every chunk of charge has the same distance away. It has that r. Okay, so I should have called it an r. Then I can come to this integration, and so there's my lambda, and then I just have an integration of ds, and of course cosine theta. Now, of course, I know what you're still thinking, that, okay, this theta changes, so I really need to write theta in terms of the ds. Otherwise, I have a harder problem, a multivariable one, and they are connected together. In fact, I will kind of remind you that the arch of a circle, a little bit of arch, ds, is theta times the radius. And so if you're talking about a infinitesimal small length, you're talking about an infinitesimal small angle. Whoops, I don't want the F, I want an R. Okay. So, putting that into this problem, I've got 2 times q times lambda over r squared. And then I'm going to integrate this ds, which I'm going to write as r d theta cosine theta evaluated from 0 to pi over 2. And so you can kind of see that really the only step I did right here was to factor this lambda out. And of course the r doesn't change, so I can pull it out and then cancel it with 1 down here. So it's 2 times Coulomb's constant times lambda over r times x squared equals. And then we've got this question, what is the integral from 0 to pi over 2 of 1 over, or not 1 over, but just 1 times cosine theta d theta evaluated from 0 to pi over 2. Now this can be a pretty hard integral. Copying an x down here. Why did I do that? So that was supposed to be the r coming out and then being crossed out. So there's no x there. That was me bringing out the r and crossing it out. Okay, and then that. But now we need to think about what is the antiderivative of cosine. And I need to think myself, sine, the derivative of sine is a cosine. Okay, so the antiderivative of a cosine is a sine. And then fortunately, that just becomes sine of pi over 2 minus sine of 0. Which the sine of pi over 2 is 1 minus the sine of 0, which is 0, which makes that all equal to 1. And so I get 2 times Coulomb's constant times lambda over r. And so there would be our And I think that's the final answer. Again, the general rules, when they don't give you numbers to put in, you should leave it in the symbols they gave you. So did they give me a Q? Yeah, but it's not in here. But it's really buried in the lambda, and they gave me a lambda. So I think I'm okay. They gave me an R, and that's okay. And Coulomb's constant. So the two that they gave me, which was the R and the lambda, I think are okay to leave the answer that way. So I'll leave it as that. I suppose my other thought was lambda, remember, when we did it back here, we said it could be the charge divided by the length. And the length is a half a circle, and so that was this over here. 1/2 of 2 pi r is pi over r. So we could write this as a Q over pi r and put that into there. But I think what we have is really what the authors wanted. All right, so 2 tough ones, a lot of calculus in there. I'll say it again, you guys started the semester off with a tough chapter and maybe a little bit of rude waking up call. Hopefully those were helpful.